Hello everyone, myself Prayag Patel, working as an assistant professor in IT/ICT department of LJ Institute of Engineering and Technology. Unit number 2, analysis of algorithm of ADA subject. We already one the topic of the second unit, best case, worst case and average case analysis. Now in today's video lecture, I will discuss about the asymptotic notations used in analysis of algorithm. Now first, what is the asymptotic notations? Asymptotic notation means big O, omega and theta considered as the asymptotic notations allow us to analyze an algorithm's running time. Means algorithm's running time can be represented using the big O, omega and theta notation. You can write the big O of n, theta of n and omega of n. Asymptotic notations is a shorthand way to represent the time complexity. Means you can represent the time complexity using these three notations. There is also known as the algorithm's growth rate. Asymptotic notations are used to for the two purposes. First is to characterize the complexity of the algorithm, and second to compare the performance of two or more algorithms solving the same problem. Means using the your big O omega theta notation, you can compare the your complexity of the some algorithm. Now consider the bound on running time. Here two bounds algorithms running time, lower bound and upper bound. Now first consider the lower bound of algorithms running time. A lower bound Ln of an algorithm defines the minimum time required. Means it is not possible to have any other algorithms whose time complexity is less than L of n. Means lower bound of algorithm means your minimum complexity. In any case, your complexity is not less than that is called the lower bound. Now upper bound, and upper bound u of n of the algorithm define the maximum time required. We can always solve the problem in at most u of n time. Time taken by a known algorithm to solve a problem with worst case input gives the upper bound. Means lower bound means your minimum time required to solve the problem. Upper bound means your maximum time required to solve the problem. Upper bound means your maximum complexity. In any case, your complexity is not greater than that is called the upper bound. Now consider the first notation as a big O notation. Big O notation represents the upper bound. Now what is the definition of big O notation? The big O notation is denoted by the big O symbol. It is a method of representing the upper bound of algorithms running time. Means we can say that it is a worst case complexity representation. For a given function g of n, we denote by big O of g of n. The set of functions big O of g of n equal to f of n. There exist positive constants c and n0 such that 0 less or equal to f of n less or equal to c into g of n. For all n0 less or equal to n. Means here consider the two functions f of n and g of n, and condition consider as a f of n less or equal to c into g of n for the constant value c and n0. G of n is a asymptotically upper bound for function f of n. F of n equal to big O of g of n, means we can write the function like this: f of n equal to big O of g of n. Implies the f of n less or equal to c into g of n. This is a condition for the big O notation. Now consider this figure for the big O notation. Here consider the f of n is less than c into g of n. So see in this figure, f of n is less than on lower side and c into g of n at upper side. Here consider the one value as a n0. So here this first part consider as a n0. What is the meaning of n0? Means before the n0 your condition will not satisfy, but after the value of n0 always your condition will be satisfied. So you can say that n0 is initial point of your condition satisfaction. So here f of n equal to big O of g of n is satisfied after the n0. Now consider the second notation, omega notation. Omega notation represents the lower bound. So definition of omega notation is, the omega notation is denoted by the symbol omega. It is a method of representing the lower bound of algorithm's running time. Means consider as a best case. For a given function g of n, we denoted by the omega of g of n. The set of functions omega g of n equal to f of n. There exist positive constants c and n0 such that 0 less or equal to c into g of n less or equal to f of n for all n0 less or equal to n. Means here we consider that this is a reverse case of big O notation. Means reverse condition. In previous case f of n is less than c into g of n. In this case c into g of n is less than f of n. G of n is asymptotically lower bound for f of n. F of n equal to omega of g of n, you can write according to this equation. An equation considered as a f of n is greater or equal to c into g of n. Now in this figure we see that c into g of n at lower side and f of n at upper side, because f of n is greater than. After your particular value, means consider as a n0, after the value of n0 you will always satisfy your condition f of n greater or equal to c into g of n. Before n0 your condition will not satisfy. Now consider the third notation, theta notation. Theta notation means consider as a same order. In theta notation, consider the definition. The theta notation is denoted by the symbol theta. By this method, the running time is between the upper bound and lower bound. For a given function g of n, we denote the theta into g of n. For the set of function theta g of n equal to f of n, there exist positive constants c1, c2 and n0 such that 0 less or equal to c1 into g of n less or equal to f of n less or equal to c2 into g of n for all n0 less or equal to n. So here consider the theta notation means combination of big O and omega notation. In big O notation, f of n is less than or equal to c into g of n, means second part. In first part, consider the omega notation, means c1 gn less or equal to f of n, consider as a omega notation. So combination of big O and omega notation consider as a theta notation. Theta g of n is a set. We can write f of n belongs to theta of g of n to indicate that f of n is a member of theta g of n. G of n is a asymptotically tight bound for f of n, means consider as a same order. F of n equal to theta g of n implies f of n equal to c into g of n. In this figure we consider our equation c1 gn less or equal to f of n less or equal to c2 into g of n. So at lower side consider the c1 into g of n, at middle position consider the f of n, and at upper position consider the c2 into g of n. After the sum value of n0, so here consider n0 as your initial point. After this point n0, your condition will be satisfied every time. So consider this is as a n0. Now summary of the big O, omega and theta notation. Big O notation means upper bound represented by big O, and main condition is f of n less or equal to c into g of n. In omega notation, condition is c into g of n less or equal to f of n, and in theta notation condition is c1 gn less or equal to f of n less or equal to c2 into g of n. So here consider these three conditions. Now first condition for f of n equal to, we can represent big O as a f of n equal to big O of g of n. We write the theta notation like f of n equal, with omega notation like this, f of n equal to omega g of n, and theta notation like f of n equal to theta g of n. Now consider the example of asymptotic notation, how you can find the complexity of your example. For example, consider the example number 1, f of n equal to n square and g of n equal to n for algorithm 1 and 2's running time. Now consider your condition one by one, means put the value of n and put the answer in this table. If we put n equal to 1, then what is the f of n? F of n equal to n square, g of n equal to n. So 1, then answer of the f of n and g of n equal to 1 and 1. If we put the answer equal to 2, for n equal to 2, f of n equal to 2 square, means for g of n equal to 2. N equal to 3, then n square equal to 9 and n equal to 3. If n equal to 4, then 16 and 4. If n equal to 5, then 25 and 5 value for the f of n and g of n respectively. Now consider your condition. F of n is less than g of n or f of n is greater or equal to g of n. Check your condition and find your notation. Big O notation, omega notation or theta notation. So here check. For 1, consider f of n equal to g of n. Yes. For 2, consider f of n is greater than g of n. For 3, f of n is greater than. For 4, f of n is greater than. For 5, f of n is greater than. So we can say that from the value n equal to 1 to all the remaining value, your answer is satisfied for the f of n greater or equal to g into n. So here consider your function as a f of n greater or equal to c into g of n. Means we can say that your notation as a omega notation. F of n satisfy your omega notation. So we can consider this example for omega notation. Now consider the second example. F of n equal to n and g of n equal to n square, means reverse condition. So find the value of each and every first function is for first algorithm and second function for second algorithm running time. So your second table consider as a value of f of n and g of n. So simply we can change the column of f of n and g of n. So here value 1, 1, 2, 4, 3, 9, 4, 16 and 5, 25 respectively for f of n and g of n. Now check your condition. Here for the first condition 1, you satisfy the condition f of n is less than c into g of n. For 2 also satisfy. For 3, 4, 5 all the condition we satisfy f of n less or equal to g of n. So we can say that f of n for the function f of n, your asymptotic notation as a big O notation means f of n equal to big O of g of n, because here satisfy the condition f of n less or equal to c into g of n. Now consider the another example. F of n equal to n square and g of n equal to 2 raised to n. Then find the value one by one. So first consider value 1, n equal to 1. Then f of n equal to 1, g of n equal to 2. For value 2, consider the here for value 1, consider the condition f of n is less than g of n. Yes. Now for the value 2, consider the value f of n equal to 4, g of n equal to 4, means f of n equal to g of n. Now for value 3, f of n 9 and g of n equal to 8. So we can say that f of n is greater than g of n. For the value 4, f of n equal to 16 and g of n equal to 16. So we can say that f of n equal to g of n. Now for value 5, f of n equal to 25, g of n equal to 32. So we can say f of n less than g of n. For value 6, consider value as a 36 and 64. Value consider equation consider as a f of n less than g of n. For value 7, 49, 128 means f of n less than g of n. So here we can say that what is the value of n0, means after which position your condition will be satisfied. So initially f of n less than g of n, then f of n equal to g of n, then f of n greater than g of n, means in first three condition no any decision is made. So here consider the next value as a from the value 4, n equal to 4, then f of n equal to g of n. Then after always f of n is less than g of n. So we can say that for the n greater or equal to 4, f of n less or equal to g of n condition is satisfied. So your value of n0 equal to 4 for your this example. Consider here two examples, f of n equal to 30n plus 8 and g of n equal to n square plus 1. So order of growth for the f of n equal to big O of n, g of n equal to n square. Now represent this complexity in a form of your chart. So here consider the value of first f of n equal to 30n plus 80. So growth of this function in this sequence as a 30n plus 8. Now growth of the second function g of n equal to n square plus n. So consider the growth of second function in red line, g of n equal to n square plus 1. So initially f of n is greater and g of n is less than. But after some time g of n is greater than the f of n. So consider this point as a n0 for your starting point. Remember this point. Here consider f of n equal to big O of g of n. In general, any big O n square function is faster growing than any big O of n function. Means here consider first function is big O of n, second function is big O of n square. Means growth of these two functions, which function is higher growth? So n square is higher growth than n. So consider the order of growth according to this. Now consider the order of growth or common order of magnitude. Means consider the different complexity. Here n, log n log n square, n cube, 2 raised to n and n factorial consider as a different complexity. Your algorithm's complexity may be any one out of this. So consider the growth of this all the complexity one by one. So if we consider the value of n equal to 4, then what is the value of log n? 2. N log n equal to 8, n square equal to 16, n cube equal to 64, 2 raised to n equal to 16 and n factorial equal to 24. Next we put the value of n equal to 16, then log n equal to 4, n log n equal to 64, then 256, then 4096, 65536, 2.09 multiply 10 raised to 30. Now consider 64, 256, 1025, 24 and 4096. For the value of n, you can consider the value of log n log n square, n cube, 2 raised to n and n factorial. Find each and every value. So after find this table, you can consider growth of your each and every complexity. Which growth is highest? So initially here consider which element increment highest is considered as a highest growth. So here consider the minimum growth as a log n, for example, because only increment by 2l value 2, 4, 6, 8 like this. Next, after the log n, consider the n. Then next growth consider as a n log n. Then next consider as a n square. Then n cube. Then 2 raised to n. Then consider the n factorial. So order of growth for this given complexity as a n log n, n log n square, n cube, 2 raised to n and n factorial. Now consider the some example for understanding the how you can arrange the order of growth. So arrange the given notation in increasing order of their values, means for their growth. For example, consider the first example, 2 raised to n, given complexity is here 2 raised to n log n square, 1, n log n factorial and n cube. Arrange this complexity into the ascending order or increasing order of their growth. So first 1, because 1 is constant and constant growth is 0. So 1 consider as a first, then log n, then n log n square, n cube, 2 raised to n and n factorial. Consider the second example. Given order is n cube, 1, n square, n log n square log n raised to 0.5. Now arrange data for the second example is first. Initially 1, then log n, then n raised to 0.5, then n log n square log n, then n cube. Third example, n factorial, 2 raised to n plus 1 factorial, 2 raised to 2n, n raised to n and n raised to log n. Arrange this data into ascending or increasing order of complexity. So here consider first is n raised to log n, then 2 raised to n, then n factorial, then n plus 1 factorial, then 2 raised to 2n, then n raised to n. Remember this for your example. Now consider the growth function for your order of growth. Maximum growth function rule. Let f and g consider as a function and consider as a n to r plus. The maximum rule say that big O f of n plus g of n equal to big O of maximum of f of n g of n. Means out of the your function f of n and g of n, if the both function are in addition form or subtraction form, then consider the maximum rate or maximum growth of your function f of n and g of n is your answer. So maximum of f of n and g of n is considered as a big O of your answer. So first example, n raised to 4 plus 100n square plus 10n plus 50. Now what is the complexity of this function? Big O of n raised to 4, because highest power of n considered as a n raised to 4. So this is your answer. In second example, 10n cube plus 2n square, then maximum n power considered as a n cube means 10n cube. So your answer is only n cube because 10 considered as a constant. So your answer is big O of n cube. In third example, n cube minus 2 raised to n, then consider maximum power as a n cube. So big O of n cube. The lower order term in a function are relatively considered as a ignorable. For example, n raised to 4 plus 100n square plus 10n plus 50 equal to n raised to 4 means all remaining term are ignorable. Consider the example of of buying the elephant and goldfish. Means your target is buying the elephant and goldfish. Now consider the total cost for buying the elephant and goldfish. Consider as a cost equal to cost of elephant plus cost of goldfish. Now consider the cost of elephant is very high and cost of goldfish is very low. So consider the lower term as a negligible or ignorable. So consider the total cost as a approximately cost of elephant, because cost of goldfish is ignorable. So here in this case, n raised to 4 100 n square 10 n plus 50, you can consider the n raised to 4 here as your growth, because remaining all term is ignorable. So in today's video lecture, I will discuss about all the asymptotic notations big O, omega and theta, how you can find the big O, omega and theta notation or compare the big O, omega and theta notation. Thank you for watching.